Creation and the country. And you're almost welcome. We'll be starting in about a minute from now. Julian, I think the time is up for us to start.
Okay, let me share my screen. Okay, well, welcome participants. Welcome to these sessions of the Nile Basin Development Forum. We're very excited to have you. This event, I think, is every 2 years, so this is always a great opportunity. I'd like to welcome you on behalf of the caretakers of the session, and those include Azeb Mersha from NBI Intro, Michael Abibi from NBI Intro, and Aloysi Odur from NBI as well, and myself, Julian Haru from the University of Manchester. So you're most welcome. On behalf of all of us, we're very pleased to welcome you here. We have an exciting technical program of 5 talks. Then we'll have the keynote speaker who's coming from North America, so they're waking up, going to wake up early to present in the last slot. And then we will have a half-an-hour discussion at the end. So that is the program for today, and we'll be able to have questions either spoken or through the text chat, where you've hopefully all introduced yourselves. So let me start then by having our opening session speaker. We have the director of the Nile Basin Initiative, Eastern Nile Technical Regional Office, NBI Intro, Dr. Salih Hamad, from the director of NBI Intro, will be giving us just a few minutes of welcome remarks and motivating this webinar on new analytical tools to understand and plan water energy food system linkages in East Africa. This is part of 2 sessions on water energy linkages. So hopefully, Dr. Hamad, you're there with us?
Yes,
Can
yes.
you introduce us? Thank you.
Okay, thank you very much, Dr. Julian. Glad to have all of you here. Welcome all who are attending this important session. Dear distinguished panelists, our keynote speaker, paper presenters, ladies and gentlemen, it is my great honor and privilege to be present here in this session this afternoon. As we are all aware, water and energy are vital for our socio-economic development. Water is needed for food production, energy production, livelihood. Energy is crucial for households, industry, and provision of and treatment of water for community and agricultural development. They are closely interdependent and key prerequisites for our existence. Global projections indicate that demand for freshwater energy and food will increase significantly over the next decades under the pressure of population growth and mobility, economic development, international trade, urbanization, and cultural and technological change, in addition to climate change. Therefore, it has become ever more important to understand the linkage between them, to anticipate future stress points, and to implement policies, technologies, and practices that soundly address the associated risks. Articles in Google dealing with water, energy, and food nexus have increased exponentially from few articles 10 years ago to over 22.4 million nowadays. This reflects the importance of these drivers. There are three reasons for that. First, there is a strong linkage between the water, energy, and food nexus and the global program of achieving this SDGs. For example, SDG number 6 of water is closely related to number 2 of no hunger or food, to number 7 of energy, and both influence 2 and 6 to continue to number 2 and 6 will have contribution to number 3 of good health, and to number 7 of clean energy, and all contribute to number 8 of economic growth, and so on, to link almost directly or indirectly all the SDGs. The second reason is that to increase the awareness about the economic risk included in the nexus. And the third reason is to drive to promote the nexus as a new framework for global policy debate about the linkage between resource use and development, and ultimately about the means to facilitate sustainable development. Although the issue of water, energy, and food nexus is global, it is more pronounced in developing regions, such as the Eastern Nile economics, where ambitious development plans are putting stress on all these resources while supply is not keeping up. Water resources are already under significant pressure for irrigation and drainage water demand. The Eastern Nile Irrigation and Drainage Studies Operative Regional Assessment concluded in 2010 had estimated that the total irrigated area in the sub-basin was about 5.5 million hectares, and planned to irrigate in the coming 10 to 20 years more 3.8 million hectares, with demand goes beyond the available surface water resource of the sub-basin. Hydropower plays a significant role in both water and food production systems. It currently contribute about 23% of energy generation installed capacity in the Eastern Nile countries, and there is a huge untapped hydropower potential in the eastern region, particularly in Ethiopia, and it is expected, if developed, to significantly contribute to the development of the other two drivers. Moreover, the challenge of water availability will be further compounded by climate change, which will call for significant adaptation mechanism. In sub-Saharan Africa, including Eastern Nile, most countries already face climate variability that is many times greater than the predicted change in climate. But climate change will make things worse, and therefore the need to support adaptation strategies is more urgent. Conceptually, and from the transboundary context, let me pose the following question. What the transboundary context brings to the nexus? What the nexus approach brings to the transboundary context? What are the relevant skills that individual countries look to the three drivers, that is water, energy, and food, from their national, regional, or international? What are the relevant skills? What is the most relevant skill to look to these drivers from a transboundary perspective here? What is the added value of the nexus approach nationally and in transboundary context. And in practically context or practically, and recognizing significant variation in the water, energy, food sectors with multi-sectorial and multi-level processes, how can we implement this approach? What are the technical and institutional capacities we need? Should the nexus be implemented through already existing organizations like Intro or the Nile Basin, or is it better to establish new cooperation mechanisms for implementing the nexus? What is the role of basin organizations in water, energy, food nexus? What transboundary nexus networks? What transboundary networks that integrate these sectors will need to be developed? I am sure that the presentations of our distinguished experts will tackle these questions and will know more about these questions. But let me agree that a nexus approach helps us to better, or helps us to better understand the complex and dynamic relationship between water, energy, and food, so that we can manage our limited resources sustainably, taking into account different economic, social, and environmental goals. A nexus perspective forces us to think of the impacts a decision in one sector can have not only on that sector, but on multiple sectors and drivers. Based on this, we can identify trade-off and synergies that we can design, appraise, and prioritize response options and interventions. Recognizing that the Eastern Nile Technical Regional Office, INTRO, has entered into a joint project with the University of Manchester of the United Kingdom. The University of Manchester, as we know, is leading the Future Dams Research Consortium. We entered into a project to advance the work on an integrated water energy framework to evaluate resource planning, allocation, and infrastructure assets options. This initiative is supported by new and innovative web-based simulators for river basin and power system models, led by the University of Manchester, with input from Eastern Nile African Power Pool, EAPP, that is Eastern Nile Power Pool. The overarching objective of the project activities is aiming to build knowledge, capability, and capacity to address global development challenges through a system scale approach to choosing packages of human development interventions over space and time. Sustainably developing water and energy sources for multiple purposes is a key to the socio-economic development of many countries, where demands for energy, irrigation and water supply, flood control, and ecosystem services are increasing. A specific objective of this project is to design, develop, and apply a technical and economic decision-making tool for integrated water, energy, food, environment systems analysis and planning. The modeling tool will enable policymakers and planners to understand the complex interactions among multi-sectors demand for water, energy, and food, move towards more sustainable resource allocation and management strategies, and support the identification of regional investment opportunities. This will greatly contribute to attaining an MBI into strategic goals. With these words, let me welcome you again, wishing you fruitful deliberations and successful session. Thank you for your time and attention. Thank you very much. Thanks.
Wonderful, Dr. Salih Hamid. Thank you so much. That was a wonderful introduction and setting the scene for this session. So thank you very much. And having NBI Intro launch this session is most appropriate. So thank you so much. Okay, well, normally we in Nile Basin Development Forums, we have a keynote talk, but our keynote speaker we've allowed her a bit more time to appear because she's in North America, although I see that she's already here. But let's stick with the program. So we're going to have 5 technical 10-minute presentations, and right, I've noticed I haven't shown you the program, so let me quickly review that so people see the program, and then we'll start with the first talk. So here's the program. We have the opening session by Dr. Salih Hamad, which we've just heard. A wonderful presentation. So the order of presentations will be Edo from TU Delft, Atsede from East African Power Pool, Mikias from University of Manchester, Vignesh Sidharan from KTH, and then Mohammed Bashir and Alvaro Calcedia from Manchester and UCL London. That'll be followed directly by our keynote talk. Dr. Claudia Ringler from IFPRI is joining us from the East Coast of North America, and she'll be presenting the keynote talk. And then after that, we'll have a full half hour for discussion with 4 panelists from IFPRI, EAPP, NBI, and the University of Manchester. I'll introduce them when we get to the panel discussion. So right now, let's go straight to the first technical talk. We'll do them in this order. And please put your timers on and try to limit yourselves to 10-minute talk. Let's start with Edo Abraham. Welcome.
Thanks, Julian, for the introduction. See if you see my screen, I guess. Yeah.
Yes, we do. Thank you.
Oh, sorry, it's on the wrong slide. So I'm Edo Abraham. I'm an assistant professor at TU Delft, and I work on water and control systems engineering problems. And my talk would be on operational planning of water energy food infrastructure, quantifying the value of cooperation in the Eastern Nile Basin. This talk is kind of a brief of a manuscript of the same title, done in collaboration with Jeroen Verhagen, a research assistant working with me, who did most of the work. So I'm going to stay very sketchy on some technical details and just try to give an idea of what we're working towards. So I will give a motivation, scope of the work, and just show some results. It will just be a sketch, and then try to make some conclusions from it. So our goal in my group is we would like to illustrate the benefits of costs and intersectoral trade-offs in transboundary cooperation in managing water, energy, land resources, specifically in the Eastern Nile Basin. And of course, there have been lots of talks talking about the need for cooperation. And one approach of looking at it is the use of cooperative game theory, where let's say Dinar and Nigatu in this paper, for example, show the distributional aspects of cooperation. They look at how can you cooperate, for example, through water trade, under different water sharing agreement scenarios. And they look at the idea of kind of for each country to go into a grand coalition, and what are the sort of marginal benefits. And what they show is that because of the kind of the asymmetry in economic development within the region, it turns out that you can't really find sort of scenarios of cooperation that are when you redistribute the benefits equitably are beneficial for everybody. So this kind of core in the middle is empty. And so they look at externalities like sediment management and what you can gain from it in terms of harm abatement and the costs redistributing those benefits. And they show that you could actually have a non-empty core. So the suggestion is that we should look beyond water trading and think about so enlarging this cooperation so that the benefits in getting into a grand coalition could be much bigger, and therefore we can facilitate potential cooperation. So in our work, we look at free trade in agricultural products and energy as a kind of mechanism for cooperation. And so we try to show whether that will result in increased utilization of resources in terms of specializations in agriculture and energy production, and perhaps looking at also regional self-sufficiency as another aspect. So what do we do? So we propose a kind of optimization framework where the operational plans within the whole basin could be actually optimized into the future. So looking at actually gridded model representing all rain-fed agriculture and irrigated agriculture, as you can see in this network of water conveyance and storage infrastructures. Looking at in each country also kind of the demands for the different energy and food products, the interaction with global markets. Can we do substitution of imports and things like that? So we have built a model that has sufficiently detailed hydrological description, including all processes of production and consumption in the 3 countries. And this being especially explicit because we would like to attribute, let's say, economic benefits to different activities, and also looking at things like interventions in agriculture and so on. Making hard links between the different sectors as well, the food, water, energy sectors. The idea is also, can we introduce policy objectives? So we have built a large-scale optimization problem that could then be solved efficiently. And we show in the manuscript that this is possible to do. And so in such a model, the decision variables would be quite broad. You could cropping patterns across the countries, how you generate electricity and import, export agricultural goods or energy itself, and so on. To do this, also we consider multiple levels of cooperation scenarios to kind of tease out the composition of economic benefits you get from cooperation. So we look at, because it's not possible actually to also compare with, let's say, what is produced at the moment. We look at a case where we optimize per country maximum national economic benefits from the use of the infrastructure, and then go all the way to sort of playing a social planner where we redistribute resources within the whole basin. And in between, we consider things like information exchange on expected water flow from upstream countries to downstream countries. So, for example, Sudan can plan its, cropping and water energy production based on information from Ethiopia. How is this computationally structured? We use what's called a modal predictive control method, where we look at planning over 3 years, for example, with some predicted climatic conditions. And then every month, as new information becomes available, we update the plan. Yes. So you could have cropped your land and you could decide how much deficit irrigation you would have, or you could decide how to crop and so on. And we test this approach on a deterministic historic simulation because we were able to collect lots of data from the past on both consumption and also, of course, discharge and precipitation and climate conditions. So we have looked at a number of dimensions. One of them is, okay, what do the economic benefit look like per country and also regionally as we look at different levels of cooperation. So you see for Egypt up there to Ethiopia, and what we see is that as you have more and more cooperation, you go from unilateral action towards regional planning, the economic benefits increase significantly. And for Sudan, this is even more important, and we see that the contribution that comes from just information sharing is very significant. Yeah, 745 5% versus 837%. And we also look at the idea that, of course, you don't have perfect projections on climate conditions and prices and so on. So what is the value of information? So by kind of changing the information used in the optimization and the planning, and then using different information in simulation, we look at the change. And of course, there's a decrease in the benefits, but we see that the pattern is consistent. Yeah. You can also, with our tool, look at things like water productivity in irrigation. And here on the left, for the unilateral case, that the water productivity dollars per meter cubed for Egypt, it's the highest, and Ethiopia has a higher one, and for Sudan it's much lower. And this is, of course, for Ethiopia explained by the favorable environmental conditions in Ethiopia. You have low evaporation. And also we see that as you go from unilateralism to flow information and full coordination in all countries, productivity increases. And this is associated with some specialization in cropping and also the availability of information in planning. You can also have a look at the composition of cropping patterns as you go from unilateral to cooperation. And you will see that things like in Sudan, the percentage of fodder produced for export increases. In Ethiopia, there's a shift, for example, from cereals towards nuts and vegetables and things like this. So you could have a look at what this means in practice, of course. You could also look at self-sufficiency in agricultural productivity. For example, in both unilateral and coordination cases, Ethiopia could plan to sort of produce its food basket in the country. You see here up to 70% could be produced internally, but that comes with a decline, let's say, in agricultural production value, because you'd be producing things more expensively than importing. So there's this trade-off that could be analyzed per country and regionally. And what we show is that when you have coordination, this decline as you become more self-sufficient is much less. So to summarize some conclusions, a more synergetic resource use could be achieved, and it could increase economic benefits could be achieved. So you think about, let's say, a 1% shift in agricultural water use, but a 10% increase in economic gains. And through water productivity as well. And of course, how you redistribute this is not within the scope here, but this is also something else we're working towards. Increased agricultural water use efficiency through cooperation, but one could also consider about interventions and their impact here as well in a regional cooperation scenario. Trade-offs between self-sufficiency and production value can be quantified. I don't present it here, but we also look at trade-offs between irrigation and hydropower and what this looks like spatially across the basin. So another thing maybe to reflect on is the value of flow information downstream. So could this be already done using, let's say, information technology on sort of, let's say, predictions, seasonal predictions and upstream water use through satellite-based products and so on. So I'll stop here. And if you have any more questions, please get in touch.
Thank you so much, Edo. That was wonderful. And we'll take questions during the last discussion. Okay. So let's go straight to the next. Thank you, Edo. Let's go straight to the next talk. Atsede, please bring up your slides. And Atsede Endegnignu is a employee at the East African Power Pool, and she's presenting a presentation on a new tool here. So welcome, Atsede.
Thank you very much. Good afternoon, everyone. My name is Atsede Endegnignu. I'm a researcher at Eastern African Power Pool, and I'll be talking about PyN Energy Simulator and its application to the EAPP power system. So just to give an idea about my presentation, I'll give first an overview on the PyN Energy Simulator, and then I'll give an overview of the Eastern African Power Pool system, And finally, I'll show how we have modeled the EAPP system in PyEnergy tool. So PyN or PyEnergy is a flexible open source optimization tool that's used for power system analysis at regional and national levels. It's capable of performing different types of analysis, but just to mention a few, it can run techno-economic analysis of generation portfolio. It can determine optimal operation of generation assets, and it can be also used for analysis of renewable integration, taking into account variability of the renewables and the electricity demand. It is possible to model different types of generation technologies in PyN. Hydropower, including pumped storage, solar, wind, and other types of generation can be represented. And we can do different types of power system applications, such as DC OPF, economic dispatch, unique commitment, and so on. PyN was developed with the users in mind. It's expected to be used not only by researchers, but also by industry practitioners. Therefore, it's very easy to use. It has both online and offline versions, and its inputs and outputs are linked to Excel. The tool solves complex mathematical problems faster than similar tools or equivalent tools because of the C++ solvers it uses. And it's an open source software, meaning that it is free to download and use. And the source code is also available for users to modify according to their specific needs. Having said that about PyN, I will explain more about the Eastern African Power Pool. That's where I'm from. The Eastern African Power Pool, it has 11 member countries. It covers a very large geographic area with a population of over 500 million people. Its peak demand for 2020 was 58 gigawatt, but this peak demand is expected to increase significantly over the next decade because of two main reasons. First one being the economic growth in the countries in the Eastern African Power Pool. And the second one is the policies adopted by these countries to achieve 100% electrification. Currently, only Egypt and Libya have 100% electricity access, with the rest of the countries in the power pool planning to achieve universal access between 2025 and 2030. If we look at the power pool generation, it's dominated by thermal generation, but it has different types of resources available in the power pool. Natural gas is used in the north, in Egypt and Libya. Hydropower dominates in Ethiopia and Democratic Republic of Congo. And the other countries in the power pool have almost half and half thermal and hydro generation. This diverse mix of generation and natural resources mean that the marginal cost for generating power is different from country to country, creating an incentive for interconnection and power trade across borders. Currently, as you can see here in the figure, there are some of the countries that are connected with each other. The blue lines, they indicate existing interconnection, and the orange lines, they indicate interconnections that are under construction. By 2025, the entire power pool is expected to be interconnected, but there will be multiple synchronous areas as some of the connections are in high voltage DC technology. As I mentioned earlier, the power pool is dominated by thermal generation. This is because the two largest countries in the power pool, Egypt and Libya, they use fossil fuels for power generation. But the entire region is blessed with abundant renewable energy resource that has been untapped yet. And the planned expansion considers these existing renewable resources. By 2030, it's expected that hydro will double compared to today's installed capacity, and solar and wind, they will increase from 4 gigawatt today to almost 30 gigawatt in 2030. So in the future, renewables will be will have a significant share of the power pool generation mix. And other types of renewables, such as geothermal, will also have some sort of share, particularly in Ethiopia and in Kenya. So the benefits of this cross-border power exchange will be even more important with the integration of renewables, but it will also be important for the optimal operation of the power system by sharing of reserves, economic dispatch of generators, and increasing security of supply in general. So how did we model this EAPP system in the PyEnergy tool? It's a large system. It had 389 generators of different types of technologies. And for the thermal generators, fuel cost is considered in addition to carbon emissions. For the renewables, the renewable resources, the variable profiles are used for each geographic location. And operational rules for hydroelectric power plants is also considered. The transmission network had more than 6,000 bases and more than 8,000 transmission lines. And right now we have modeled 4 representative days, 1 day for each season. So as you can see here, these are the 4 days for each season, the electric demand across the region for over 24 hours period, and renewable potential for the solar and wind power plants at each location is considered in the modeling as well. So the intention is to use this model to run optimal power flow and make a comparison between the isolated power system versus the integrated power system, and to be able to see the change in operational costs, reduction in carbon emission, and reduction in demand curtailment or increased in security of supply. So with PyN, we're able to look into the power system and see its the added value of operating the system in an interconnected manner. So that was the presentation I prepared for you. Thank you for your attention.
Wonderful. Thank you so much, Atsede. And you even took 1 minute to spare. So thank you. We can win back some time on the program. So we'll keep questions for the discussion. Let's go straight to Mikasa Kishida from University of Manchester.
Are you looking at my screen?
Yes, please make it full screen. Great, thank you.
Thanks, Professor Julian. In this presentation, I'm going to talk about the integrated water energy model of the East African Power Pool. I'm a PhD student at the University of Manchester, and this presentation is a continuation of the previous presentation by Mazada. In this presentation, I'm going to cover how the water system of the East African Power Pool is connected with the energy model that was presented by Mazada. These are the contributors. At the top are the water and energy modelers. In the middle are our partners from the East African Power Pool, and from INTRO, Eastern Nile Technical Regional Office, and at the bottom are our advisors. So I have 3 main topics to cover. The first one is the East African Power Pool model, the water model. I'm going to go through and discuss about the main structure of the model. In the second, we'll introduce you the future dams integrated water energy modeling framework that we developed in the past years. And lastly, I will talk about how the East African Power Pool water model is integrated with the energy model that was discussed and presented by Azadeh. So the map shows the East African power pool member countries, the river and the transmission network. It also shows the existing and future hydropower potential of the region. With the exception of Libya, the East African power pool member countries are either partially or entirely in the Nile basin. Hydropower also plays a vital role in supplying cheap and affordable and clean energy to the region, especially to the upstream countries, with the exception of Egypt and Libya. It contributes more than 50% of the energy mix. But this country is also characterized by low electrification rates compared to the rest of the world, again, with the exception of Egypt and Libya. And the other important factor is also Nile Basin is one of the water-stressed basin of the world. Due to the less low electrification rate and due to ever increasing in electricity demand related to economic growth, there is a high initiative by the countries to develop and exploit the hydropower potential. And as explained earlier, hydropower is going to also play a critical role in supplying electricity. So, so the benefit to be gained from the integrated resource operation and investment in water energy would be a key to improve resource utilization efficiency. With related to that, an advancement in modeling tools to understand these synergies between the water and energy is indispensable. So one great example could be the Grand Ethiopian Renaissance Dam, which is shown by the big yellow rectangle on the map, where Ethiopia want to satisfy their very increasing electricity demand, while the downstream countries worried about how the feeling and long-term operation of grid will impact their water use. So the East African power pool water system, which covers, as I said, the East African member countries, it runs for 33 years from 1997 to 2002, model at monthly time step. We calibrate the model against the annual average hydropower generation and reservoir water level. The table shows the main feature of the component of the water system. We model 108 hydropower, which include the existing and future. The inflow 218 flow nodes, 52 reservoirs, and 50 demand nodes. Most of the demand, or all of the water abstractions or demand, which are irrigation and domestic water demand, are found in the Eastern Nile River Basin. So we used an open source Python library called Pyrovw, which is the fast water resource simulator, which is published. You can find the paper online. And also there is a web interface you can use. You can develop or build a water model or share or run, visualize the water resource model on the web interface. This web interface also enables multiple users to develop a water model, the same water model remotely, which makes it more suitable for a transponder river basin like the Eastern Nile or the Nile at large. So I'm going to talk about the future dams integrated water energy modeling framework. I would like to linger a little bit about the approaches widely used to integrate water energy models. On the right, you see a simple water and energy network where you have a reservoir, multiple reservoir with supplies hydropower, with hydropower generation and also supplies irrigation and water supply. On the right side is a simple energy model with 3 paths, and the two models are integrated with hydropower. So there are 2 approaches to link the water and energy. The soft linked approach, where you run the water and energy system sequentially but independently, and pass back and forth data. So you can run the water energy model until a defined iteration criteria, or you can have one-way, two-way communication, or a number of iteration. This soft linking has the advantage that you can use a rule-based operating rule. For instance, if your reservoir follows a certain rule, then soft linking is the most appropriate one. And on the other hand, we have the hard linking approach, where you combine the water and energy model in one big linear program, and you optimize the 2 systems. So in most cases, the objective is either to minimize the cost or maximize the benefit, mostly economical benefits. So the hard linking approach inherently assumes a well-established water energy market, and you need to assign cost and benefit for each water or energy resource. We use a Python, again, open source Python framework called Pinsum, which is a component-based resource framework to integrate the two systems. So this figure shows how we integrate the water energy system of the East African power pool. We have the water model run and pass hydropower to the energy model, and we at monthly time step we use soft linked two-way communication to integrate the 2 system. We select soft linking approach because most of the reservoirs in the region are operated using a rule-based operating rule, and there is no well-established water and energy market. So lastly, this shows the schematic shows the integrated water energy model of the East African power pool. So we have around 1,525 buses, this one is a simplified network. As I mentioned, that is more than 7,000 buses. That was a detailed network, but in this case, simplified network. 331 thermal generators, 45 wind and 12 solar panels, and 108 hydropower plants. So also show the water system components as well. So the model runs for 30 years at monthly time step. This is all from my side. Thank you.
Wonderful. Thank you so much, Mikias. And let's go straight away to our next speaker, and that's Vinesh Sidharan from KTH. Welcome, Vinesh.
Hi, I'm going to share my screen now. Yeah, hi, good afternoon. My name is Vignesh. I'm a researcher at the Division of Energy Systems at KTH here in Stockholm, Sweden. And I work in a research group which looks into the interlinkages between climate, land, energy, and water systems, or abbreviated as CLUES. Today, I will present a study on Uganda that uses an integrated setup of the different systems described earlier. And this is a combined study developed by me and a few others at KTH, and also some counterparts at United Nations Department of Economic and Social Affairs, UNDESA, and Simon Fraser University in Canada. The aim of this case study is to analyze three resource systems, namely energy, water, and land, under one shell in an integrated manner, and explore the ripple or cross-propagation effects of policies in one system and how it affects the others, especially in the case of Uganda in this context. To give some context here, Uganda's forest cover as a share of total land area has dropped from 24% in 1990 to about 9% in 2015, which is about 36,000 square kilometers of area lost to deforestation. Two main reasons contribute to this particular change. One being cutting down of forests for firewood, and the other being the deforestation for agricultural expansion, and also grazing, cattle grazing. It's also interesting to note at the same time that biomass, primarily firewood, constitutes about 80% of the total final energy consumption in Uganda. And of late, in order to meet the targets under the SDG 7 goals, there is an increasing push to reduce the dependency on woody biomass in Uganda. And additionally, ambitious irrigation plans and an increase in per capita water consumption, water and energy consumption are expected to result in a more stress on the different systems. Here, in order to explore the cross-system implications of a Ugandan national biomass strategy on the reducing the use of firewood, we developed two scenarios to look into. One, a baseline scenario where the energy, land, energy, and water systems have their business as usual trend going up to 2050. And another sustainable development scenario where there is a shift to sustainable energy consumption. In the scenario, the biomass consumption, which stands now at about 80%, is expected to go down to 50% and in 2050, and the rest is and it's compensated by an increase in electricity demand. A simplistic assumption is made there. The model itself is developed using the open source energy modeling system, which is primarily an energy systems modeling framework developed here at KTH, but now has been used extensively to include water and land related aspects with some climatic links as well. The model itself consists of detailed catchment specific land use and land cover classifications, site-specific agroclimatically attainable crop yield values, and water deficit maps were also included as part of this analysis from the Global Agroecological Zoning Database. In this model, there is a competition for water and energy resources amongst the different supply and demand sectors. Overall, the objective here is basically to simulate a policy on biomass use in Uganda and analyze its impact on other interlinked resource systems. Since there's not much time to go into the model itself, I will go directly into the results and explain them. This is the line graph here that shows the total deforested woodland and forest area between the two different scenarios as described earlier, the baseline and the sustainable development scenario. So in the sustainable development scenario with the reduced biomass, about 7,250 square kilometers of woodland and forest area is expected to be conserved, which is about 3% of the total land area in the country itself. Getting some results on the electricity supply sector. The cost of electricity generation for the two analyzed scenarios is presented in the primary y-axis of this particular figure. In the same figure, the difference in installed electricity generation capacity between the sustainable development and baseline scenarios is presented which is basically the secondary y-axis. The policy change, the reduction in biomass, is expected to result in marginally lower electricity costs in the 20s, which partially could be attributed to higher utilization of power plants in the sustainable development scenario. Another reason is that in the baseline, the demand is actually lower and the system has an overcapacity in hydropower. Also, a significant increase in the cost of electricity generation is expected towards the end of the modeling period, which is primarily due to increased fossil fuel usage to meet the higher electricity demands in the sustainable development scenario. we also developed some emission-related specifications in the model. So in this figure, the difference in emissions trajectories between the two scenarios is presented. The orange bars basically represent the CO2 released from the electricity supply sector due to the increase in fossil usage. The difference in the scenarios, that's what is presented here. And the green bars represent the extra CO2 that could be sequestered by uncut forests and woodlands. So about cumulatively, due to the policy change, about 50 million tons of CO2 could be sequestered in the uncut forests and woodlands. However, about 33 million tons cumulatively of CO2 is expected to be released by the power sector alone. Moving to some land and water systems related impacts. The electricity and water consumption in the agricultural sector is presented on the graphs on the figures to the left. The increase in cost of electricity generation due to the policy change is expected to result in lowering the consumption in the agricultural sector, which in turn reduces the water used for irrigation purposes. This leads to a shift in agricultural water use types as shown in the figure to the right. By 2050, approximately about 10,000 square kilometers of land, which were expected to be irrigated in the baseline scenario, are replaced by a higher 15,000 square kilometers of rain-fed land in the sustainable development scenario. It was interesting to notice that during the modeling process that the shift primarily happened in three main staple crops in the country, mainly the plantain, matoke bananas, maize, and cassava. However, the coffee cultivation, which is predominantly irrigated in going until 2050, does not shift to a rain-fed type of cultivation. Yep. So this is just to this slide shows the spatial coverage that goes into the model. This particular slide shows the variation in land cover from the start of the modeling period to the end until 2050. For different land cover types and for different crop types as well under the cultivated land. This is just to show that the model actually accounts for the spatial, can actually account for a lot of spatial detail. So at present, it uses 10 kilometer by 10 kilometer grid cell values from the global agroecological zoning database, of course, and then they are clustered based on the average agroclimatically attainable yields. Yep. So yeah, just to give a very simple conclusion that the study showed that one policy change in the biomass consumption in the energy system may lead to ripple effects resulting in higher power sector emissions that could influence or induce unforeseen changes in agricultural water use types. Therefore, a mandatory understanding of such cross-system impacts during sectoral policy formulation will actually help mitigate future regrets, financial primarily. I'll just breeze through the presentation. So in case if you have any questions, and also if you want to share models, I'd be happy to respond. Thank you.
Thank you so much, Vinesh. Right on time. In fact, 9 minutes and a half. Thanks so much. That was brilliant talk. And let's have our last 10-minute talk by Mohammed Bashir of Future Dams.
Thank you. Thank you very much for having me today. So I'm going to present about a modeling framework for integrating river system models with macroeconomies in an iterative process based on a single piece of software. And I'm going to show an application for that on the Eastern Nile Basin and Eastern Nile Basin countries, Ethiopia, Sudan, and Egypt in this case. So my introduction will have four main points. I'll start with a general introduction, then I'll dig a little bit into the modeling framework, and then I will show how I apply that to the Eastern Nile Basin. I will finish with some conclusions. So it's well known that there are strong interlinkages and interdependencies between water, energy, food, and economy systems. Especially when you look at river basins, for example, water availability impacts aggregated agriculture and municipal water supplies and industries and hydropower generation. But at the same time, the economic performance determines how much water, energy, and food are needed. But there are also some interlinkages between different sectors that impacts the economy. So for example, if you have low water availability for food production, that means food-related industries will have less need for energy, which should directly impact how water is used within the river system and impact the whole economy. So the question here is, if we can fully model these interlinkages and interdependencies, can that lead to better water, energy, food economy system decisions? So for that, we developed this modeling framework which links economy models with river system models. So this is a generic framework. It has two components, an economic component and a river system component. So the way the framework works is, first of all, the economy component is based on the IFPRI standard CGE model, and the river system component is based on Pyrovw, which is a generic Python library for simulating resource system networks. So the way the framework works is that the economy first runs based on its external drivers to determine the changes to water, energy, to water and to irrigation and municipal and industrial water demands, but also the demand for electricity and also non-hydropower generation capacity based on investment behavior within the economy. And then that's passed to the river system model, which has a lumped representation of non-hydro energy generation technologies. But then again, these changes in demands are used to inform the river system model before it performs its allocation. But here it's also worth mentioning that the economy runs on an annual time step and the river system model runs on finer time steps. So that means within each annual time step, you've got multiple time steps within the river system model. Once the river system model determines resource allocation and then it determines how much water actually can be supplied to the economy and pass that information back to the economy model, which go through another iteration to determine these demands. So all this process is happening within one annual time step. That means if you are running a model over multiple years, you've got quite a few iterations within one annual time step until the two models reach to some sort of convergence in which there is no improvement in model estimates anymore, and then that's considered a solution to the annual time step. So at that stage, the economy model and the river system model reach to their solution for that specific annual time step, and then move to the next annual time step. So as I mentioned earlier, we're using different tools to develop this framework. The common characteristic of these different tools is that they're all open source. So we are using the IFPRI standard CGE model, which is open source and publicly available. We're also using Pyrovw, which is an open source Python library. We're using PinSim, which is a Python network simulation framework. And PinSim is used to connect the different models and manage their information exchange and their time stepping. So on the application of that framework to the Eastern Nile Basin, so we've developed, calibrated and validated an Eastern Nile River System model, which includes quite a detailed representation of water inflows and water uses. Sorry, excuse me. And I will show you a schematic of that model in a bit. But we also developed computable general equilibrium models, which are economy models for Egypt, Ethiopia, and Sudan. And then we connected the river system model and the economy models of the three countries through PinSim. So the models talk to each other. So that you've got the water side of things and you have the economy side of things, but also the economy models can talk to each other through PinSim, and that's quite useful in simulating commodity trade, for example, between different countries. As I mentioned earlier, the non-hydropower electricity generation technologies are represented in a lumped way within the Eastern Nile River System model. This is a general structure of how of the production and consumption structures of the economy models. I'm not going to go into detail in that, but in general, the production is done based on a three-level process in which you combine different factors of input and different intermediate inputs to produce outputs that's done by different economic activities, but also you've got the consumption side in which households and divide their consumption budgets based on certain commodity groups, and then they have certain elasticity to shift between different commodities depending on economic performance. The river system model was calibrated and validated over 1970 to 2002. What you see on the schematic you see on the right side, that is a schematic of the Eastern Nile River System model. It has a monthly time step, and it includes 162 inflow nodes, a number of demand nodes, all major reservoirs and dams and wetlands. But then we also, in order to conduct some analysis and to examine some future scenarios, we generated some river flow traces. We did that using the index exponential method. So we generated 102 river flow traces to capture hydrologic uncertainty, and we generated those traces based on the 1901 to 2002 data. And each one of the traces has a 30-year-long temporal coverage. Now, I just want to show you some sample results. I'm not really going to dig into detail about the scenarios that we examined and looked at, but here's just some sample results for how the type of results that can be generated from this framework. So what you see on the right-hand side here, this is so for example, for Egypt, this is a time series of the change in the Egyptian GDP based on different ways that for operating the Grand Ethiopian Renaissance Dam, which is located in Ethiopia. So here we're comparing two ways of operating the GERD, but we're examining that across multiple hydrologic scenarios. So the gray lines you see here, each one of them represent one hydrologic scenario for how the future could be. So we're capturing hydrologic uncertainty, but we're also looking at the change in economic performance. So this change is triggered by the change in the water system through that iterative framework that I presented earlier. On the right-hand side, you see also the change in GDP for Ethiopia under the same conditions. So here you can fully capture the impact on different countries in terms of economic performance. This is just an example for results, but CGE models are known to produce quite a variety of outputs, ranging from the output of different sectors, exports, imports, the income of different households, and so on. And all these can be generated considering hydrologic uncertainties and different ways to operate the water system. So I just want to finish off with 2 points. Modeling the interdependence of river systems and macroeconomies could result in better management decisions because that helps fully capture the interactions between the economies and the physical systems in a more realistic way. And lastly, as I mentioned, the non-hydro technologies in this framework is represented using a lumped, simplified approach and using specialized power system models like the one Mikias and Atsede presented could help improve the accuracy of this modeling framework and better capture the interlinkages between power systems and macroeconomies. Thank you. I'll leave it here.
Oh, wonderful. Okay, thanks so much, Mohammed. So that concludes our 5 short talks of 10 minutes each. And now I'm delighted to introduce our keynote speaker, Claudia Ringler from IFPRI. Claudia, please go ahead and you have a 15-minute slot. Thanks so much. I think you're still on mute, Claudia.
Yeah, thank you very much for the invitation to this session this morning. I think I've listened to really excellent talks that all capture different but important components of water, energy, and food linkages in East Africa's Nile Basin. I will not provide any detailed tool descriptions, really just directly focus on a series of solutions along the water, energy, food interface that are essential and important for the Nile Basin's future. And I think the urgency of action has been already very well described in terms of population growth, growing water stresses, climate change, etc. So unfortunately, my presentation, of course, is okay, frozen, but it's moving. So I'll start with a series of global solutions and then move to the region and finally to local solutions. And all of them, of course, have to work together. They're all interconnected. And they should ideally all move in the same direction of improving water security, energy security, food security, while also improving environmental outcomes. I think that's really the goal that the Nile Basin Initiative is striving towards, and of course each of the member countries and all of the connected and shared users of these Nile Basin resources. So the first solution that hasn't come up yet this morning focuses on simply maintaining open trade with the rest of the world. So the Nile Basin as a region, but each of the Nile Basin countries really should try to maintain open trade regimes. We've seen some modeling of food self-sufficiency scenarios in the earlier presentations. Those are generally suboptimal in terms of achieving food and water security, because they just take an undue amount of natural resources. So the trends are growing food import dependency across the Nile Basin countries. I think that's not surprising, and everyone living there has probably seen that. Open trade can facilitate food imports, especially those agricultural commodities that require a lot of water and land resources should be reconsidered, and even more so those that generate limited incomes or no nutrition. Sugarcane is right there, generates incomes but no nutrition. Rice generates some income, some nutrition, but much less so than animal source foods, vegetables and fruits. And of course, open trade regimes are even more crucial as a result of climate change. We've already heard from the ENTRO director that climate change and climate variability is already dramatically affecting the region. So just to underline the point, this just shows the change in demand for meat products, cereals, fruits and vegetables, and roots and tubers between 2010 and 2050. We see an increase in the basin demand for these commodities by it's a more than doubling change of demand. So this is quite dramatic. And you can imagine, we've seen the presentation on the dramatic decline in forest area in Uganda. That, of course, affects water quality, water quantity, water resources. If we continue like that, we basically would have no forest resources left in the basin just to meet this food demand, if we continue business as usual pathway. Therefore, we project a dramatic increase in net food crop imports. So this is the change between 2020, which is basically last year, and 2050, considering climate change. This is a historic cereal import dependency, so that's back to 2010. And basically, the darker the color, the higher the import dependency just for cereals. And basically, those colors are getting darker as the years pass. The second solution or recommendation is to not only keep open trade regimes, but to at the same time proactively support national, regional, and global climate change adaptation investments, and of course also joint adaptation and mitigation when and where feasible. And a simple calculation, just looking at the changes in food prices as a result of climate change alone. So we basically see growing food prices. I mean, not just recently because of COVID-19, but there is a long-term slow increase in the cost of food and agricultural commodities as a result of climate change. That alone would result in a net loss of $255 billion between 2020 and 2050 for Nile Basin countries. Consumers lose out because they have to pay a lot more for agricultural commodities. And it also means that the demand for more nutritious commodities is depressed. Avoiding these losses really requires proactive adaptation investments. And there's a lot. Several have already been mentioned: watershed rehabilitation, improved soil and water management, to some extent expansion of irrigation where it's sustainable, improved irrigation management, and better institutions. So obviously the largest benefits can be achieved if not only the Nile Basin accelerates adaptation investments, but also the rest of the world. So now some regional solutions. So a couple years ago, we did an e-survey over the internet, but also to some extent face-to-face, asking technical bureaucrats in the key water, energy, environment, and agriculture agencies in Sudan, Egypt, and Ethiopia, to what extent they're happy with national cooperation across water, energy, food, and environmental sectors, as well across the Eastern Nile Basin. And what you can see here is just one response to the question: ongoing regional cooperation is adequate to minimize trade-offs and exploit synergies. And the answer basically, the majority of respondents disagree. So they all see a lot of potential for cooperation as soon as you move to the technical level. So there is really scope to do more. We've already heard about the importance of regional energy trading. Trading here, electricity trading outperforms a reference scenario without trading. It also can lower system costs. It helps increase the sources of energy, especially if we ensure, or if we put very explicit targets for renewable energy sources. And of course, diversification as a result of climate change, but also because of other geopolitical considerations, diversification is key to improve energy security, and of course also to reduce greenhouse gas emissions. Goes right back to food prices, to water security, etc. So as you all know, this is all very closely interlinked. But beyond Nexus cooperation across the agencies responsible for energy, water, agriculture, and the environment, we also need a direct strengthening of cooperation just for water resources. That's why we have the Nile Basin Initiative. These previous presentations have already shown that there are some trade-offs if single sector and single country strategies are being pursued, and there are lots of benefits if cooperation is instead favored. And of course, the more infrastructure you put in place, the more cooperation can improve outcomes, unsurprisingly. And right now, quite a bit of additional infrastructure is being constructed, and not just large dams, but we also talk about dramatic increases in irrigation in much of Eastern Africa. So another area for regional cooperation is rehabilitation of watersheds across the entire Nile Basin. It, of course, increases the shelf life of gray infrastructure, increases resilience, reduces flood drought risks, and also the impacts once these droughts and floods do come, because they will increase in number and intensity. It can support transboundary cooperation. Many of these fragile watersheds do cross borders. It can directly increase agricultural productivity and, of course, improve and ensure important ecosystem functions. So again, I guess a plea to the modelers to increasingly consider environmental outcomes and ecosystem functions in the modeling. In terms of local solutions, a key one, of course, is to sustainably and equitably expand irrigation. We know it increases rural incomes, employment, especially in the dry season. It fuels agricultural growth and improves nutrition, and can improve also domestic water access in rural areas. We've done a study on the change in net food import dependency from accelerated irrigation. And of course, that's quite dramatic in sub-Saharan Africa, given that current irrigation is very low, irrigation as a share of total production. There's a sustainable potential of at least 3 million hectares in the Nile Basin. Of course, the plans are generally much more dramatic, but much more needs to be done on improving the sustainability of both existing and planned irrigation. So to do that, we need to build more capacity on reducing, minimizing crop water use. There are a lot of technologies out there that are currently not in use in the basin. Costs are coming down. So definitely more effort needs to be done by all the countries on that topic. So it's also important to consider strengthening groundwater governance in parallel with groundwater development. A lot of the new irrigation is directly developed by farmers themselves, and they increasingly use groundwater resources. It's also important to even now focus on improving and reducing agricultural water pollution. The growth is fastest in Africa. And finally, it's important to monitor and evaluate benefit streams, not just for male farmers who tend to benefit more directly from irrigation, but to also to assess how women's access and benefits from irrigation can be strengthened. This is just the study on the impact of expanded irrigation investment on net trade in the entire sub-Saharan Africa. And you can see through irrigation, we can reduce net food import dependency, or we can reduce net imports to a third. In terms of groundwater governance, we are currently implementing a pilot study in Ethiopia. And what we've seen there is that there are generally no rules about groundwater use. So farmers just go ahead, dig their wells, choose their crops. And there's a lot of also investment by outsiders. And in fact, governments try to accelerate groundwater development. And that is certainly all good, but we do need some institutions to not go down the path of some South Asian places like Northwest India, where we have dramatic depletion of groundwater resources. So promoting institutions for groundwater use is an important intervention that needs to be accelerated. We talk about the nexus, and we've heard several presentations on the importance of clean energy access in rural areas. It supports water security and food security. It's just being restated here. There's a direct linkage between energy expansion in rural areas and agricultural productivity. And of course, it can certainly improve important ecosystem functions. Again, think about the map in Uganda with the very traumatic deforestation. So clean energy directly supports groundwater irrigation. It can reduce deforestation, various erosion events. It can also, of course, support water infiltration, but electricity access alone is not necessarily sufficient to reduce fuel wood use for cooking. So we need additional interventions to basically ensure that we get a rural energy transition towards more cleaner solutions. And of course, clean energy access can also support agro-processing. Conclusions. So I think what I've been trying to do is just summarize opportunities at global, regional, and local levels that can improve water, energy, food security, and environmental outcomes. A lot of them have already been discussed, so I'm really just summarizing. Single sector strategies are almost always suboptimal, or they underperform. Cooperation is essential. But at the same time, trade-offs are real, and they will certainly grow with population and income growth and climate change. And that's why we have the important role of the Nile Basin Initiative, and even this event where people come together, share the latest research results, help guide policymakers and technical specialists and experts on trade-off and synergy analysis. It's important, I think, to develop more open access data going forward. There is a lot of open access material, but it's still very difficult to find, especially for policymakers who would like to use these for decisions. Data sharing remains a challenge. The monitoring of impacts of various infrastructures, including green infrastructures, such as reforested watersheds, on key human and planetary livelihood outcomes it's improving, but there are still big challenges. And as long as we don't know the benefits, we will not make the investments. Thank you very much.
Okay, wonderful. Well, we've had some fascinating talks there. Let's go straight to our panel discussion, and let me bring up the program to introduce the panelists. Great, so here's our session and our panelists. Unfortunately, we have a slight internet problem in East Africa, which means our panelist from the East African Power Pool is not able to join us, Dr. Haitham. So, but luckily, Director Salih Hamad from NBI Entro has been willing to join the panel. So why don't we just start with a very short 1-minute statement by the panelists, just to give your overall first impressions, and maybe you can hint at what you think your first question might be if you've already thought of one. But just a short 1-minute statement, just to give your overall view. And because, why don't we start with Director Hamad, since he introduced the session. Director Hamad, how were these talks interesting? Can you just give us a quick 1-minute opening statement?
Thank you, Dr. Julian. I would like to thank the presenters. This is a very, very interesting session and very interesting also presentations. They give very good insight about this water, energy, and food drivers, which are really the whole theme about the Nile basin, if you can say. As intro director, I am interested in, the cooperation in general. As you know, if countries are to take unilateral way of development, that eventually will end up in competition, and as you know, competition will lead to tensions, and tensions will lead to insecurity in the region, and that is, we don't like that path. Now, the question, as you know, that this region is very sensitive in terms of the resources in general, water, energy, and food, and also in the hydropolitics, very sensitive. How can we, and it is, you see that even when we are focusing on water resources, there is a lot of problems and challenges. How can we, when we are looking from the transboundary context, how can we take the three drivers together in the transboundary cooperation? This is, I see this is a very central question. How can we bring the Nile basin countries, also in Eastern Nile countries, all together through a cooperative action on the three drivers, that is water, energy, and food. And I think this question, the best one to reflect on is Dr. Claudia. She's working in a very pioneer institute. I would like to ask her just to give her reflection on how can we put a strategy, a cooperative strategy to take the three drivers together in the Nile Basin region. Thank you very much.
Okay, thank you, Director Hamad from NBI Intro. So Claudia, don't answer just yet, because Claudia is in a difficult situation of being both a panelist and a presenter, which means technically she could ask herself questions, but that would be embarrassing, so hopefully she won't. Let's quickly go to Azeb Mersha from NBI Intro. Obviously, your director just gave a question there, Azeb, but maybe you have some technical question. Azeb is a modeler for many years. So any opening statement from you, Azeb? What was your overall impression on the work presented?
Thank you, Julian. We have seen all the interesting presentation, and what I can add is from our experience, what we have done so far as regarding to planning and modeling tools in addressing difficult issues of the Nile Basin. Just to give you an insight, as you know, we have been saying through series of the webinars, the complexity of issues of the Nile Basin, and also giving us a lot of opportunity for future cooperation and collaboration of the basin countries. In years, lots of models and planning tools have been developed addressing different issues of the basin, like flood, drought, climate change, irrigation and drainage, power trade, watershed management. But all these studies, if you see, they give us valuable information, but these findings have not been integrated across sectors to yield direction of like giving wider basin level water resource optimization or efficiency. So recognizing this gap in Neil's Hub and intro, what we have done is multi-sectoral investment opportunity analysis that identified coordinated water infrastructure investment strategy for the basin that promotes shared sustainable economic growth and development in the region. The multi-sectoral investment opportunity analysis, what it does is takes the basin as one system and try to undertake water resource analysis that promote cooperation and investment planning that consider water scarcity of the basin, and also consider socio-economic and environmental implication of such investment for the future. The other one major accomplishment of the Nile Basin is developing Nile Basin decision support system as a decision-making tool that helps the Nile Basin country to make a common analytical based work, and also exchange of knowledge base and data between the countries, and to dialogue and to find a win-win solution for the basin and for a sustainable planning. And when you talk about planning, it's all about knowing the current situation and forecasting for the future and deciding how to prepare for it. So what we recently have done is we have done strategic analysis, water resource strategic analysis, which was done basin-wide, considering all the Nile Basin countries, that inform repair and dialogue on the selected current and emerging challenges of the transboundary water resource and managed at basin and sub-basin level, and seeing what are the different trade-off analysis have been done. So what we have done in the strategic analysis is we estimate project future water availability under the current climate and with climate change, and we quantify likely water deficits and explore different strategic options for balancing water supply and demand. So this, for this, we have different drivers: population growth, rise in water demand, and having different future investments in the different location of the basin. And we try to assess using different indicators: use efficiency, equity, economy, feasibility, food security, and mitigation for food and drought resilience to climate change are our major indicators. So we don't only focus on the scientific facts and technical analysis, but we try to contribute preparing policy papers and decision-making different knowledge products. I think I'll stop here. Thank you.
Great. Okay, thank you so much. It's great to hear all the things that are going on there at NBI Intro and with NBI in the region. We're lucky on the panel to have a pure power systems engineer, and that's lecturer Eduardo Martinez Cesena, who goes by Alex. Alex, any high level, very short comments on your impressions on these presentations we just heard?
Thank you, Julian. I'll try to be short. I mean, from my perspective, I focus a lot on the models, but what I like from this more than the modeling is just the having the discussion. Because we started this project as people who didn't know what other researchers, other people working in different fields were doing. So just having these discussions, trying to understand the problem from a different perspective is quite valuable for us. Also because that allows us to develop models taking into consideration that type of feedback. So I'm quite happy to see the different perspectives. And looking at the question you have here, are these things creating confusion or insights? It's part of both. We're trying to get insights about what part of the nexus, what interactions are confusing, what are the parts that we need to clarify either with the models or with discussions. So I'll leave it like that. I think yes, having these interactions is going to be quite valuable from different perspectives.
Okay, that's great, Alex. So Alex is like I said, a power systems academic, and he's always specialized in capacity expansion or planning models for power. So it's been great to have him involved in this, in the water energy nexus analysis. He's on future dams. And the last but not least, we have our panel member and speaker, Claudia. Claudia, you hinted at your impression on the other talks. But if you want to, 1 or 2 minutes now, if you want to just say a more general statement and maybe hint at 1 or 2 questions if you have them. And then, of course, thanks, Alex, we have these questions. You know, does all this advanced modeling create insights or confusion? You can also, if you'd like, Claudia.
Yeah, thanks. Yes, there's so many things to talk about. And we also have the question from Dr. Salih Hamad. Yeah, so yes, I mean, let's first go on the confusion question. If model results are not presented in a policy relevant way, then they often cause confusion. And of course, not all models lead to the same results. Also, I have to say, you know, generally for the Nile Basin, in terms of the need for cooperation, in terms of the interlinkage between water, energy, and food security, in terms of the benefits of trading, certainly for energy, agriculture is a little bit more challenging, but also feasible. Water is obviously shared already. Yeah. So I think that the key trends and the key developments are quite clear, and the models are certainly agreeing on these. There are sometimes some, I think, you know, differences in results in terms of the strengths of the trade-offs and the exact amount, absolute values of benefits accruing to different countries from different investment interventions. But I think that is personally, you know, it's fine. That's normal. We don't all use the same data. We don't all use the same modeling mechanisms. So I think the policy results overlap in general. The challenge is that, you know, countries still drive national strategies, and that not all of the national goals overlap 100% with, you know, regional cooperation, you know, policy results. And a lot of these models, as I said, the results are just not presented in a sufficiently policy relevant way. Many of these results are generated at universities. They don't reach policymakers, or at least at the technical level. So obviously we don't want ministers, actually now we have ministers in Sudan and Ethiopia and probably in some of the other countries who could easily do these models themselves, but they're very busy. This being said, so we just need to be able to reach the technical levels that report back to the ministers to try to you know, help generate some impact in terms of more joint investment planning. So joint across sectors. And there, I guess my point would be to take ecosystem functions and services a bit more explicitly, incorporate them into the models. So basically consider more also, I guess, you know, food security, equity. I think there was a comment in the chat box, in the Q&A as well. So yeah, those are some of the things the models could do, but you know, the key really is come up with, you know, what are your 5 3 to 5 policy conclusions, and be very transparent in terms of how they're being derived. And just to Dr. Sali, how can we make a difference? So each of the countries in the Nile Basin have their own national economic planning mechanisms, their national investment strategies. They might be 3 years or 5 years. They're being updated. So go into those, see where they coincide with trends, in upstream and downstream countries. Where can we make a small change in these national plans that are really at the end of the day driving investments in agriculture, in energy, and also in water security? Where can we make small changes to generate win-win outcomes across the basin? And I think these small changes are feasible, and as long as there are benefits for each of the countries in addition to transboundary benefits, so I think we can advance those. And I think a big and a growing argument in all of this will be climate change. It's so clear that if we don't adapt, if we don't mitigate, the impact will affect every person, every food consumer, everyone who wants to rely on hydroelectricity, just because the climate change impacts will be so traumatic and affecting everyone. Thank you.
Okay, thanks so much, Claudia. That was a lot of content in just the 2 minutes. Thank you. So why don't we, the floor is open to ask questions to the presenters. We do have a chat box. Why don't, hopefully the 5 presenters and Claudia feel free to have a look at question and answers. They're in Zoom. We also have just a normal chat box. But just to kick us off, I'm wondering if one of our 4 panelists have maybe a specific question or a burning question to one specific speaker, or perhaps more than one. Let me just give that opportunity now. So now we have about 15 minutes to just ask questions. They can come from the people in the audience, and they can come from our panelists. So I'm just going to be open to whichever I see here. I have the chat open, the Q&A session open, and then we can also listen by voice. So maybe just kick us off. Any panelists did any of the presentations bring up a specific question?
I mean, I'd say there's a bunch of questions in the Q&A. For example, there was a question of why South Sudan is not reflected in the power pool. It would be good to get an answer on that, because it's a very important question. Every time we talk about the Eastern Nile, the question on South Sudan comes up. Why is it not being modeled? Why is it not being considered? I think that's an important question we need to hear an answer on. And there is also another question on who takes decisions on, for example, reservoir operations. Is it always a water agency? Is it done higher up at the state level, given that water operation of reservoir infrastructure is especially in the Nile Basin, but elsewhere as well, in transboundary basin, it can have international implications. So who is in charge? I don't know who can answer those 2 questions, but they're important.
Yeah, maybe Atsede from East African Power Pool. Atsede, you just started recently as the East African Power Pool, and maybe there are several people, several of our speakers are from the region. Does anyone have an idea why South Sudan, maybe that's a data issue, or will we, does anyone know if South Sudan is formally part of the East African Power Pool?
I can take that question, actually.
Okay.
South Sudan is not an Eastern African Power Pool member, at least not yet. So that's why it was not included in my presentation. But in some of the planning studies, it's included in the studies because it's connected to the Sudan power system. And in some of our studies, we also look into the interconnected systems that are beyond the power pool. So in the south, the power pool is connected to Zambia. In the north is Jordan and so on. So it is included in those type of studies.
Okay, wonderful. Yes, so thanks, Claudia, for bringing our attention to the Q&A. We do, I did my PhD in California, where most of the questions and discussion were always involving lawyers. That's not always the case around the world. So we're lucky to have Bettina here, who's a lawyer. She asked the question Claudia mentioned, just an institutional question. Is it state agencies or reservoir owners? So there's a question there about institutional drivers behind decisions. I'm wondering if maybe any of the panelists or any of the speakers from the East African countries want to venture a few answers to those. We can just have a few quick answers. Mohammed, you're familiar with the institutions.
Yeah, thanks for this question. Well, I think the question of who operates different infrastructure, I think that differs from one country to another. But I think in general, it's more, at least in the Eastern Nile, it's more done by government institutions. So I think such kind of models, power system or water system models, can be useful to coordinate planning of all infrastructures by different government entities that are responsible for operating these infrastructures.
Okay, thank you, Mohammed. I also want to give the opportunity to Director Hamad from Nile Basin Initiative Entro office, who's the director of that organization. Director Hamad, does this question make you think of any? Do you have maybe a high-level view on this? And that was for Dr. Salih Hamad. I don't know if he's still able to be with us.
Yeah, sorry, I was out of the internet.
Oh, no worries, no worries. So we just got a question, Director Hamad, from a legal specialist, a lawyer, and she was wondering about the institutional basis for the decision making. Obviously, NBI Entro is quite an important and unique player. We have Bashir just reminded us that many decisions are made, or all decisions are made really on the country level, but there are different organizations like NBI Entro who, are also a player in the Nile. So maybe, so from a question from a legal specialist asking about the institutions, do you want to maybe make a comment about the contributions that organizations like NBI Entro can make?
Yes, sure. The NBI has a very clear institutional and decision-making organism. We have, as a Nile Basin Review, we have the NileCom, that is the Nile Ministers of Water. That is the highest decision-making level. And then, and also we have as the SAP, that is Subsidiary Action Program level, that is the Eastern Nile and the NileCom. We have the INCOM, that is the Eastern Nile Ministers of Water level. And then under these, we have the Technical Advisory Committee. For example, in the Eastern Nile, we have 4 countries. Unfortunately, Egypt is now freezing, but we have the 3 active, other 3 countries are active. We have this Technical Advisory Committee. It composed of 3 high-level decision makers or high-level technical staff from each country. We submit everything, for work plan, everything to them, and they will take approve all the type of activities that we have should be approved from this level, and then the Technical Advisory Committee recommend their decisions to the INCOM, and that is the final decision which will come to intro for implementation. Of course, we have a lot of task force committees and so on, different projects. Those are mainly, it is sort of stakeholders stakeholders' participation in the decisions or in the implementation of different projects. So we take also those recommendations, but at the end, the whole project, all recommendations should go to the technical advisory committee, and from there to the INCOM or the NILCOM, where the final decision will be taken. Also, the Nile Basin in recent years, they have also introduced the head of states, and I think they have made one meeting at Uganda. I think that is in 2017 or something like that. But that one is not a regular one. So, but generally, the problem is that the whole setting of the MBI is still a temporary setting. We hope that when countries agree on a legal setting, then the whole MBI setting will be a permanent session. But now it is going smooth. It's going smooth up to now, no problem. Thank you.
Yes, thank you so much, Director Hamad. So Bettina Geisler, one of our guests, you got some good answers there. Certainly there's institutional complexity and the system is evolving. We had another question from Tesfaye Kidane, who was asking about climate change impacts. And so what I thought we could do now, we also got a question or a challenge from Claudia about could ecosystems and environmental services be more considered more explicitly in the modeling. So why don't we combine those two questions? So the consideration of uncertainty and climate change, and then the consideration of ecosystems and the environment. You can answer one or both, but you only have 1 minute. So why don't we go through our 5 speakers in the order of presentation. So let's start with Edo. And you can pick one topic or do very quickly on both, but you only have 1 minute. Do you feel like your modeling tool can handle ecosystem services and climate change uncertainty? And what challenges do those bring? Unfortunately, we have less than 10 minutes left, so please be very brief in your answers. Let's try to go through the 5. Thank you.
Well, I think the answer is the latter is probably easier to model that's climate uncertainty than ecosystem services. But on smaller scales, I mean, we have done some work on quantifying ecosystem services and sort of looking at, you know, how you allocate to that and the distributional impact on communities, etc. But when you're looking at the scale of the Eastern Nile Basin, that's a little bit difficult. So the answer would be you can, and there are also on the climate uncertainty side, how to include that explicitly in decision making. And then also looking at the distributional impacts of like who takes responsibility if you're sharing information, you have uncertainty and so on. There are still some open questions there that we're looking at. So it's an important question. I'll stop here.
Okay. Thank you so much, Edu. He showed us the way how to present you could do a PhD on that, but he answered in 1 minute. Thank you. Let's go to Atsede.
Sorry, what was the question?
Yeah, so Atsede, you can pick the question. You either have, do you think your model can handle climate change uncertainty? Or you can pick the question, can your model handle ecosystem services and a better representation of the environmental benefits?
I'll pick the first one. Climate change uncertainty. The model takes into account some level of climate data. So how accurate would that be in the context of future prediction of the climate change? That's to be analyzed, but it takes into consideration the climate change. So that's my answer.
Okay, great. Yes, it's a supply-demand model. Okay, great. Okay, next one is Mikias.
Yeah, as said, modeling the ecosystem dimension is a little bit complex due to the shortage of data, but our water simulator simulate the environment, the water allocation for the riverine ecosystem. We can integrate that in the water allocation. But from the climate change and uncertainty side, we can model how climate change impact both the water and the power system using our integrated framework in detail.
Okay, thank you, Mikias. Vignesh.
Hi. Yeah, probably both the questions. The models that we use, yes, they can account for climate change uncertainty, especially as that said, they mentioned, depending upon the granularity in the input data, in climatic data. However, I think more work needs to be done on how uniform the climate change impacts can be applied across water, energy, and food sector and agricultural sectors to improve the uniform impact, to represent the uniform way in which climate impacts are across the sectors. That needs to be some work done on them. In terms of environmental ecosystem services, I think the only consideration that we do now is minimum environmental flows. And of course, there are 200 different ways to calculate minimum environmental flows. So we do take that into account, but still lots of work to be done there. Thank you.
Okay, thank you, Vignesh. Wonderful. And Mohammed, last one.
Yeah, so I'm going to take the climate change one from the economy modeling perspective. So within economy models, we consider the socioeconomic pathways to simulate different ways of actions from an economic perspective. So we follow the different socioeconomic pathways to look at how these pathways impact economic performance, but again, then we also have estimates for how economies can impact the climate in terms of emissions from different sectors and different outputs from different sectors and their use of fossil fuel related commodities. That's all. Thanks.
Okay, wonderful. Very concise. Okay, we have we have exactly 4 minutes left, and we have 4 panelists. So why don't we turn to the panelists in the same order as they made their initial statements, and please make a final statement. It can be about what you learned today, what you think we should do in the future. It can be anything, but it has to be 1 minute. So please, Director Salih Hamad, can you start us off?
You are closing it?
Yes, so we're just closing. We're doing closing comments. We only have 4 minutes left. So
yeah, okay.
Yeah, so if you just want to give the last minute your overall impressions.
Thank you very much. I think first, let me thank our all presenters for these very interesting presentations. And I think the issue is very important for the region. And we are focusing, of course, in the water, but as you know, water is a cross-cutting for the others. If you are talking about the energy or talking about the food, water is the essential part. So our efforts here will continue in all the three. We are always open to cooperate with different organizations to promote our objective is to bring the whole region, the countries of the whole region into a cooperative activities, so that we can optimize the use of our resources here. And among them, or the main of them, are the water and energy and the food. So that is our overall. So we will continue in Intro. Our office will continue to cooperate, to participate through the different projects, so that we can bring our countries together for the benefit of all the people of the whole region. Let me also thank, in this respect, the organizers, our mediators, our partners from University of Manchester. We would like to assure you that we will continue this ongoing, and we are open to new projects that will serve the same objective of optimizing the use of our regional resources. Thank you very much.
Okay, thank you very much, Director Salih Hamad. I just realized maybe we should have let Director Hamad have the last word, but we still have 3 panelists for your 1-minute wrap up. And next we have Azeb. Azeb, any last impressions or last recommendations?
Thank you, Julian. Yes. One thing I can say is having one sectoral analysis is not beneficiary, and having a kind of nexus approach which integrates all the different sectors and synergize, and having an optimized water use and efficiency a way forward, and to have more manageable trade-offs analysis. This kind of studies will encourage the countries to cooperate more if you have more findings, not only focusing on the water, but having analysis on virtual water trade and giving economic terms into different sectors will give the countries more perspective, which enhance cooperation and collaboration for the future. That's all I can say. Thank you.
Okay, wonderful, Azeb. Thanks so much. And just 2 minutes left here. So Alex Martinez Cesena.
Thanks, Julian. I'll keep it short. So thank you for the feedback. I think we're going to be focusing on trying to present the results in a more policy-oriented manner. And we're also going to try to account more for climate. And so we will bring on board all the feedback that you gave us, and we'll try to improve the tools accordingly.
Okay, wonderful. That was very concise. And we have just 1 minute left for our keynote speaker, Claudia Ringler from IFPRI. You have the final word here, your last impressions.
Yeah, just thanks really to everyone for giving excellent presentations, also for everyone participating. I mean, it's just great to see all the work that's being done by ENTRO and the Nile Basin Initiative. It's all, I think, going in the right direction, and also really future dams. I was very impressed by all these presentations. Great work in just very few years. I hope that that this will continue in some form or other, that we do see sustainability, capacity building. Obviously, you're building a lot of capacity, so that we can try to really influence the key policymakers, these national development plans. Bringing the economic modeling tools in, I think, is excellent, and it's really the way to go to reach ministers of finance who, and treasury and so forth, who have the purse strings. Opening them up to these cross-sectoral impacts of any investment decision, not only in their own country, but also in other countries. And again, bringing the urgency of climate change, the urgency of increased food demand. I mean, it's more than doubling, it's very, it really does change how water and land resources are used in the basin. And I think getting this urgency to policymakers, we have to do a better job there. And I think everyone, participants, presenters, panelists, policymakers, technocrats, I mean, we're all called upon to do a better job here. Yeah, and thanks again. It was an excellent session. Thank you.
Okay, great, Claudia. So that was definitely the last word. That was inspirational and very appropriate. So thank you. I just want to say that we have a session with a lot of the East, West, South, and East African power pool. It's a water energy session, and it's Thursday morning in 2 days. So we hope to see you for that second water energy session. And I'll just end by thanking the caretakers of the session. That's Michael Abibi, Aloysi Odur, Azed Mersha, and me, Julian. So thanks so much. So the session is ended, just 2 minutes over, and we hope to see you on Thursday. Thank you. Bye.
Thank you.
Thank you. Bye.